It's a real privilege for me to be here. Don't hold it against me. They got my master's up the road. It was a good experience for me, and like I said, it's a privilege for me to be here. Some of the great scientists doing this type of work are here at the University of Arizona, so I'm humbled too to be here. I want to talk about the geologic history of water on Mars, and not as a necessarily a topic, but I do want to talk about geology. I do want to talk about history. I do want to talk about water, and I want to talk about Mars. And I want to start off the talk by just showing this particular landscape here. Now, I think those of us who do planetary science have gotten a little comfortable, jaded. We forget how remarkable this landscape is. Now, to look at it, if we were to take this image outside and show it to people walking down the street, they wouldn't necessarily think very much of it. It looks like a desert environment, maybe an arroyo outside of Tucson or something. If you saw this, you'd say, yeah, that was something carved by water, rainfall, no big deal. It's not that remarkable, but it is remarkable because it's on Mars. And it makes a difference, and the context is everything. And the last 50 years from discovering these features and trying to explain how they actually got there has just been an odyssey, a real journey, and I want to take you through some of that today. So my talk today will go into the history of these discoveries, the early observations, to put these observations, the interpretations of the observations, into context with what we understood about Mars and the solar system at the time. I want to talk about the geologic features that record the history of water on Mars and the proposed processes, including modified impact craters, valley networks, really briefly about outflow channels, and some of the additional evidence that we're now getting from remarkable instruments such as Alfred's high-rise camera. I want to summarize our current understanding, what I think is not necessarily the paradigm, at least a really good working hypothesis to what has happened. And then it's always important to talk about whatever it is that you're doing in terms of its importance. So I want to, if I have time, to talk about that. And then because we do have students in the audience, and I'm like 2/3 through my career at this point, I have more ideas than I will ever be able to work on. Throw out some ideas, some outstanding problems, and if anybody sees that as being exciting, come talk to me and maybe we can set up something to come work at the Smithsonian. So first, some history. Mars is a really cool looking planet when you look at it through a telescope. It's not like Venus, it's covered in clouds all the time. It's not like Mercury, it's so close to the sun, it makes it hard to look at. And it's not like Jupiter in that it does have a solid surface to it. It's a cool thing to look at. You see these different albedo patterns, you see polar caps to it. If you look at it through the seasons, astronomers saw these albedo patterns changing through time, which kind of suggests that what we were looking at might be vegetation on the surface, waxing and waning as the seasons change, because Mars has, like the Earth, has seasons to it. But it was this Italian astronomer, Giovanni Schiaparelli, who saw these features crisscrossing Mars, connecting the dark albedo features, and he called them in Italian canali, which translates into English as channels, but it's much easier to say canals than channels. Channels is sort of an innocuous feature, something that nature may have made. Canali is something different, and that really piqued the interest of pretty much an amateur astronomer, Percival Lowell, who did his work up at the Lowell Observatory a few hours away from here. He was convinced that canals were something much different. You have to keep in mind at that period in time, the United States had taken building the Panama Canal over from the French, and that was sort of the big public works problem. That was the cutting edge of technology. Here's some people to scale over here on the edge of this canal that they're trying to dig out. The Panama Canal is only about 50 miles long, but it connects the two biggest oceans on our planet. And people could read accounts of what was happening down there in Panama in the newspaper, how many people were dying from malaria, how much progress that they had made. This is a big topic. The Suez Canal had been built earlier. Now they're talking about the Panama Canal. how much more advanced had the Martians have to be to build canals that stretch for thousands of miles across their planet. Now, the other thing that we thought we understood at that period in time was that as you move away from the sun, the planets were older. And keep in mind that the theory of evolution was a new scientific theory that had come out at that period of time. So the idea that Mars was older than the Earth, therefore more evolved, suggested that, if we're looking at Mars and we're seeing basically this dying planet, this evolved planet where the oceans have dried up and gone away, and you have vegetation and potentially intelligent life struggling to survive, if we're looking at them, they must be looking back at us and seeing what a awesome place that we have with beaches and palm trees and stuff like that. Why wouldn't they come and attack the Earth, invade us, take over our planet? It was Lowell's 3 books, Mars and Its Canals, and Mars is the Abode of Life, were the inspiration for H.G. Wells' book on War of the Worlds. And this Lowellian idea is what really dominated our thinking up until the spacecraft age, the space age in the beginning in the 1960s when we sent Mariner 4 to Mars. Now, there were papers that were published prior to the Mariner 4 mission that suggested that there was multispectral evidence that the dark patches on Mars were vegetation. And we were going to see, these wheat fields maybe blowing in the wind and everything. So here we are sending our first spacecraft to Mars. And can you imagine how disappointed some of the scientists must have been to have seen this image? It's one of the first images returned from Mars. And we're seeing a cratered landscape not unlike the moon. But it was the geomorphologists in the room that sat there and they looked at these craters and they said, wait a minute, those craters don't look like the craters we're seeing on the moon. Here's Copernicus. Copernicus has this raised rim, ejecta associated with it, a central peak. That's not what we're seeing here on Mars. We're seeing craters that don't have central peaks. They have flat floors. I don't really see the ejecta to them. They've been sort of modified somehow or another. What was going on? Well, there's people like McGill and Wise that sat there and said, well, there are degrees of modification that have taken place of these impact craters. And then you had Ray Arvidsson sat down and did this classification that showed that there are different stages of modification in these craters. And it also, by the way, is consistent with crater diameter, suggesting that modification was occurring as new craters were forming throughout the early history of Mars. Well, in 1971, we sent the Mariner 9 spacecraft and we put something into orbit. So now we could study the entire surface. And Mariner 9 got into orbit around Mars during the middle of one of the global dust storms. And this dust storm is the explanation for why those albedo deposits waxed and waned over time. We learned at that moment that Mars is enveloped in global dust storms periodically that hide those albedo surfaces from us. And at the time, it had a lot of surface features too. But it also told the geologists that aeolian activity is probably the dominant geologic process occurring on Mars today. Now, the other thing that was coming out about this same period of time too is models of the evolution of the sun. And it's basic, simple Newtonian physics that suggests that the luminosity of the sun increases as the sun gets older. Basically, you're burning the hydrogen, it's going to helium, the sun has to grow hotter and brighter in order to burn this new material that it's creating for itself. And it was people like Sagan and Mullen that pointed out, it's like, wait a minute, if you go back and you integrate what the sun's luminosity was like back during the early history of our planet, we're doomed. The sun was not bright enough to get surface temperatures warm enough to allow liquid water to exist on the surface, yet there was all this geologic evidence suggesting that there was liquid water on the surface. In fact, there's also biologic evidence that there's liquid water on the surface because life started on our planet, about over 4 billion years ago. So what they suggested was early Earth's atmosphere must have been different. It must have contained some sort of greenhouse gases in order to warm the surface temperatures above freezing. This works okay for the Earth. Mars has the same problem. But because it's further away from the sun, the luminosity effect from the faint young sun is even more dramatic. And the idea of having any kind of liquid water on the surface is almost doomed, because the climate modelers have been telling us for decades they can't warm the surface temperatures of Mars high enough to get liquid water to exist on the surface. So you put that into context with these modified impact craters and the idea that aeolian processes is a dominant geologic process. You had people explaining the morphology of these craters with dust deposits, blanketing the craters, burying them up to their crater rim crest. This is a paradigm that existed pretty much in the 70s and the 80s. And the other alternative hypothesis to this was that with Mariner 9, we discovered that there were huge volcanoes there. In fact, most of the northern plains is dominated by volcanic deposits. So the idea was maybe some of these lava flows had buried impact craters too up to the crater rim crest. So it was either some sort of aggradational process that was responsible for crater modification. So I'm going to talk about the geologic features and their proposed processes that we have for the evidence of the history of liquid water on Mars. So go back to the modified impact craters. Here are the lists of proposed processes. They're all aggradational, some sort of depositional process. Aeolian airfall, lava flows, and now we have these icy highlands models somehow or another is kind of the current climate models that we're all working with. It's all aggradational stuff. It all requires deposits that are of variable thickness, and that's where aggradational processes fail, because craters' diameters are different, their rim heights are different. You need deposits of various thicknesses to bury a rim height depending on the crater's diameter. Otherwise, it doesn't work. Here are craters that have been buried by lava flow deposits. That's not the morphology of modified impact craters that we're seeing. You still have a central peak or pit. You still have a sharp rim to them. The ejecta is gone, but you still see everything else from the crater. These craters haven't been modified. They've just been buried. Here are craters that have buried in the northern plains of Mars, up near the North Pole. These craters, you can still see the rim. You can see the crater rim shape sticking out. That's not what an airfall deposit does either. And then now you have the icy highlands model, which has been sort of the latest iteration of these aggradational processes. This is a paper by Weiss and Head, published in 2016. And so they're trying to explain crater morphology again by some sort of ice deposits that's occurring. So here you have increasing diameters. This model applies, you have the increasing diameters going to the right, but you have a deposit of a finite thickness. So this finite thickness doesn't explain craters at different crater diameters. You have, the model requires a constant thickness of ice to explain the missing smaller diameter craters. We know that craters 5 kilometers in diameter or smaller are missing from the crater population. But then you also have to add ice to the surface over time to explain how it is that you're modifying new craters as they're forming. So it's ad hoc. And then finally, you have top-down melting of exposed ice gullies, which they suggest, from transient warming events or whatever. The problem with this top-down melting idea is that you don't get water flowing fast enough to take away the large blocks of ejecta. Some are, with a crater that's 30, 40 kilometers in diameter, you have ejecta blocks that are the size of the house. This top-down melting doesn't produce water fast enough and long enough to break down the ejecta and move the blocks of material away that is necessary. And it doesn't explain the morphology of modified craters that we're seeing. So to kind of go back again and talk about the types of the stages of crater modification that are preserved in the population of craters in the Martian highlands. You start off by what we call a type A crater in our 90s papers. These are fresh craters. They have the sharp rim to them, the central peak or pit. Ejecta can be seen associated with these type of craters. These transition into type B craters where you can still see the ejecta to them, but the ejecta has typically been eroded by gullies, valley network systems. The central peak or pit has disappeared pretty quickly. You have a flat floor to that crater. Gale crater is an example of sort of a the beginning stages of a type B type of crater. I just throw that out there to give you a little bit of context. This is a type C crater. The rim now is pretty much gone. It's sort of still there, but you're starting to fill more of the crater interior. You back wasted the crater. The crater is starting to enlarge, and sometimes it is, let me see if I can point this in the right direction. Sometimes you get these scallops, retreats of the craters in places. The eject is completely gone. Again, a flat floor. They're shallower, too, than they would be for the crater diameter. And then type D impact craters is basically like God came along with a cookie cutter, and you just have these circular holes in the ground right now, steep-sided, no ejecta, no rim to them. And then eventually these craters, it's different, again, to point out the fact that there are different sizes of craters in these stages of modification. And then you have the type E type of craters where the rim gets breached and you get filling from material that is being distributed from the surrounding landscape. The other thing to keep in mind about modified impact craters too is that they are pretty much a global feature. You don't see them in the northern plains, but anywhere in the highlands you look where you have Noachian age material, you will find modified impact craters. So whatever was responsible for modifying these impact craters is more of a global process and not confined to the equatorial regions. So all of these observations combined suggest it wasn't an aggradational process at all. It was an erosional process. Those craters were eroded by something. And to get at what that something was, you have to understand what erosional processes are. And there are basically two end-member type of processes. There's diffusion, where material is separated or spread apart, and there's advective, where material is concentrated, is brought together. Okay? Both processes end up having unique characteristics whenever they've modified a landscape. And we understand that, we know the physics, we can apply that to understanding the topography and the morphometry of these modified impact craters. So let's talk about diffusion. This dispersive process is essentially equivalent to mass wasting. It requires steeper gradients with increasing area. You have linear diffusional creep, and then you also get what's called slope failure at a critical angle. You guys have heard the angle of repose, right? That's when you can't stack material up anymore and the slopes fail. That's called nonlinear diffusional creep. This is a dominant erosional process on the moon, and I'll show you an example of that in a minute. On Mars, it's important to keep in mind that diffusional processes are going to work slightly differently because of the lower gravity. There's empirical data that suggests that the angle of repose is slightly higher on Mars. So this is a Chesley-Bonestell painting of the moon that was made during the 1950s. And the idea back then was because the moon was an airless body, you don't have any weathering processes that occur. But the Earth the Earth-Moon system passes through a cloud of dust that is generated when comets basically hit the orbit of Mars. They start shedding off material, lots of dust particles. You guys have heard of meteor showers. We're passing through that material all the time, and those micrometeorites bombard the moon constantly. They act just like little raindrops hitting the surface. So instead of seeing that really sharp landscape that we thought during the 1950s, once we got to the moon and started exploring it, we saw that there really aren't any sharp features, that there is weathering that occurs on the moon from micrometeorite bombardment. This diffusional process erodes impact craters and also hills like this at the Apollo 15 landing site. The other type of diffusional process is raindrops, splash, hitting the surface, like this storm out in Lyon, France. That will disperse material across a landscape. And then another type of diffusional process to keep in mind is solifluction. We've looked carefully for evidence for solifluction at the equatorial areas of Mars. You do see evidence perhaps of solifluction at the mid to higher latitudes on Mars. That's not a process that we see at the equatorial regions. And then we also see evidence for nonlinear diffusional creep in places. You do get some occasional landslides and stuff occurring. Now the other type of erosional process is advection process, concentrative process. Advective processes involve a fluid. So yes, you can get advective processes that occur with aeolian transport. Fluvial processes are much more efficient. The efficiency of advective processes increases with the increase in surface area. Basically, the larger your catchment basin is, the more powerful your stream is going to be. There are some, well, let me talk about, there are two types of conditions. There's transport limited conditions, meaning you have so much material sitting around, but you don't have enough, say, available water to move that stuff. An example would be the Australian outback, where you have a huge erg deposit, a huge sand deposit that just sitting there, and it's a desert environment. It never rains hard enough to move all of that sand all at once. Then you have detachment limited conditions. Basically, you've gotten down to bedrock, and the amount of erosion that you're able to do is limited by how much you can detach that material off the surface. This equation over here, I don't want to scare people away. Some people can read this in their sleep and understand what it's saying. P has different values depending on the grain size of materials. So Martian conditions, because of the lower gravity, it's more efficient at carrying sand. If we take, the Salt River from Phoenix, I forget the name of the river here in Tucson, but if we were to transport it to Mars and not change anything about it, because of the lower gravity, it would do a better job at carrying sand-sized material, slightly more efficient at carrying sand-sized material, because the sand doesn't weigh as much on Mars as it does here on the Earth. But as you get to larger grain sizes, the weight of the water becomes important, so it's less efficient at eroding bedrock. And examples of, well, what did I say here? Weathering. Okay, so this stuff requires weathering or lots of water in order to move the sand on Mars. Here's an example of an advective process on the Earth, a catchment basin and some streams, and we see that on Mars as well. So how do we get about trying to put these erosional processes in context with what it is that we're seeing with crater modifications? We have the MOLA data. We didn't want to use just the gridded data because the gridding, the kriging algorithm actually kind of softens some of the surface slopes that are actually diagnostic of some of these processes. So what Alan Howard and I did was developed a technique for actually using the point data, the PEDR data from MOLA, and bending those things into these little radial bends. We're able to do statistical analysis of the elevation values represented by those shot values and get kind of a cumulative profile of what that crater looks like. We do it from the center of the crater outward. Everything's put into radial coordinates. And then for the simplicity, I've just kind of done a mirror image. We applied a 1D landscape evolution model to the crater morphometry that we were able to extract from the MOLA data to see what types of processes were responsible. And overwhelmingly, what we saw was a combination of both fluvial, advective processes and diffusional processes. The easiest explanation for that, guys, is that there was rainfall on Mars, and it rained hard enough for that material to concentrate, move across the surface, and transport that sediment away. The dark line in this photograph is a fresh impact crater. That was where our model started. We applied varying amounts of advective and diffusional processes. We did other things like control the rate of weathering and also added aggradational processes, aeolian land airfall deposits to this stuff as a way of testing everything. But a fresh crater is this dark crater. You hit it with a number of iterations beginning with the red down to the light blue. You can see how the crater begins to infill. Either this, initially the central peak or pit is eroded, but eventually it gets buried from all the material that is coming off the edge of the crater. This line right here is actually a modified impact crater, and it fits with our model output perfectly. So this crater had a crater diameter of, what do we got here, about 34 kilometers in diameter, and increased in diameter by, well, that's not 34, that's 12, 15, 26, and it increased to about 28 kilometers in diameter. So you had about 2 kilometers of back wasting enlargement to that crater, and all that material was transported to the center of that impact crater. And we did see some evidence for diffusional craters. The output, there was some additional infilling that you usually see with these diffusional craters. And the thinking now is that maybe these are craters that were buried by ejecta from, say, like Hellas or Argyre too. And those are just arrows pointing out the discrepancy. Eventually, Alan made this 1D model into a 2D model, so what we can do is add impact craters to a landscape, a synthetic landscape, and erode those craters over time. And the output from those models matches the morphology of the modified impact craters throughout most of the highlands pretty well. So to summarize, the proposed processes for modified impact craters all require, the aggradational processes all require deposits of variable thicknesses. They're ad hoc. They don't explain the morphology of what we're seeing. Degradation, erosion, explains the stages of morphologic preservation. Erosion was a long-lived event throughout the Noachian. New craters are forming as this process is continuing. It explains the size-frequency distribution curves. Basically, you've eradicated anything smaller than 5 kilometers in diameter. It's been pretty much completely eroded. It scales with crater diameter, meaning that smaller diameter craters erode faster than larger crater diameters, and we're seeing that happen too. And it's supported by the physics, basically, landscape evolution models. So moving into valley networks, you have proposed processes, hydrothermal, impact melt, a higher heat flow, maybe in the early history of Mars, groundwater sapping, which is supported by the drainage densities and also some of the morphology that we're seeing. And now we have this ice deposits, top-down melting, which has really been set forth by climate models. So the hydrothermal circulation models suggest that the impact melt from an impacting crater will melt the local ground ice and cause hot springs to form. You can kind of see this maybe with some of the larger craters that you see valley networks kind of streaming off of them. The problem is that these are short-lived events. You know, the impact melt is not going to be around for more than, say, tens to, at the most, hundreds of years. You have to have a mechanism for feeding that again. You have to have a recharge mechanism, otherwise that process will shut off. You're going to desiccate all the ice in the area, and even if you have the impact melt, you're not going to have enough water there to do any kind of work. And then again, it has to break down the larger particles and transport them away. It's really difficult to see how that's going to work. And keep in mind, too, that there's a large amount of erosion associated with some of these valley network systems. This is Parana Vallis. It's 350 kilometers long. This is the Grand Canyon at the same scale. All right? That's a huge amount of erosion that's taken place just for this one valley network system. That is really hard to do with something like hydrothermal melting without having some sort of recharge mechanism. Now, this is Naniti Valley. It's probably one of the best candidates for a sapping channel in that you don't have any kind of tributary systems feeding into it. It maintains its uniform width over a long distance. It's very similar morphologically to, say, some of the channel systems that we have in the canyonlands up in Utah, which is sort of the inspiration for invoking groundwater sapping. What is happening here, though, that we're coming to appreciate is the strong rock over weak rock stratigraphy that you have in this area. Basically, what you have to do is erode through the upper layer of very strong rock to get into the weaker stuff, and then once you do that, you can erode the weaker stuff very easily, and it gives you this sort of sapping channel morphology to it. And look closely here, you see river channels going into the headwater areas of these sapping channels too. So yeah, you do get some sapping, some seepage that occurs at the base of these things, but you don't release water fast enough through those systems, through that ground, through that rock. The permeability is just too high to allow significant amount of water to occur. Most of the erosion occurs from the top down by surface runoff on the surface. And then once we got higher resolution data post-Viking, we could see evidence for these little stream channels emptying into the headwater areas of some of these things that look like sapping channels, these amphitheater heads, suggesting that they were also the result of some sort of strung over weak stratigraphy. The other thing too is that if you go into Hawaii, like Waipio Valley, you have this layered cake stratigraphy of basaltic rock. And basaltic rock, especially layered cake stratigraphy like that, has the ability to have very sharp slopes to them. So it stands up very well under erosion. So now we have the Icy Highlands model, which is some of the output from Robbins Wordsworth and Francois Forget's 3D climate models, where they're not able to get the surface temperatures warm enough to allow surface liquid water to exist on the surface. Instead, what they're seeing is that the cratered highlands of Mars were essentially glaciated, and in their model you have transient warming events that allows that ice sheet to melt and retreat and go backwards over time. This is sort of well, Robin would say it's the current paradigm. It's sort of the competing model to a warmer, wetter Mars. The problem that we have with this idea that you've glaciated the entire highlands, though, is that you don't see any morphologic evidence for that ice sheet there. You see the valley network system, but where's the evidence for all the glaciation that should have accompanied any of this model that they're suggesting? Well, Jim Head has argued, well, you had a cold-based glacier. And if you have a cold-based glacier, the ground is basically a frozen solid to that glacier, and no work gets done to it. All right? But then you have this transient warming event that causes that glacier now to melt and form the valley network system. That doesn't work. You have three different types of glaciers. You have a polar glacier, which is completely frozen. And that's what he's arguing here. That ice is completely frozen. Nothing's going to happen to it. But then you got to get that completely frozen ice into some sort of transient warming event where you get a subpolar type of glacier where you have summer melting at the surface. But it also occurs at the base. You can't just melt an ice cap at the surface. You also have to have it melting at the base too. So as soon as you switch over to that, you now have a wet base glacier that should be capable of doing some sort of work and modification of the landscape. So that's ad hoc. And then you move into a temperate glacier, which we're not arguing for necessarily, where you have consistent above freezing temperatures, but the surface is frozen during the wintertime. So this top-down melting scenario doesn't work. Glacial ice would have to transition between these types, resulting in at least some landscape modification. And the truth is, erosion and landscape modification occurs in all types of glaciers. Cold-based glacier isn't the answer. You can go to Antarctica and see where the ice sheet is actually modifying the subsurface topography. We have plenty of evidence for glacial events in both North America and Asia and in Europe too. And in those instances, you see landscape modification. For example, a glacier will come in there and actually move the position of a river channel. So if there's any type of melting that's occurring at the base of this glacier, it's not going to necessarily follow the topography. These these diversion channels aren't anything that we see on Mars. Instead, what happens is the valley network systems follow the topography constantly. In this particular instance, too, you see these valley network systems are actually being impeded by this erodic crater rim here. They have to concentrate and breach this crater rim in order to continue to flow downhill. If there was an ice sheet here that was melting, you would expect these valley networks to transect that surface topography no problem at all. If you do a D8 algorithm, basically if you look at the topography and follow the surrounding 8 pixels and pick the lowest ones and integrate that over time or over the spatial area of your digital elevation model, you can extract the position of water flow across a landscape. And in every case, valley networks follow the topography. That's not what we're seeing here on Mars. And then there is some evidence where there's been cold-based glaciers on the Earth, and they end up producing landscapes that are dominated by tors. And then there's even this paper about cold-based glaciers that suggests that furthermore accumulating evidence suggests that geomorphologists should abandon the assumption that cold-based glaciers do not slide and abrade their beds. Now, Jim had told me that he was one of the reviewers of this paper, and they were only talking about, you know, a few inches of material that's getting moved around. It doesn't matter. You're still going to get landscape modification that is occurring that we don't see preserved in the Martian highlands. That evidence just isn't there for any type of glaciation having occurred. So valley networks, proposed processes, hydrothermals, too short-lived of an event to do the amount of work necessary. Groundwater sapping, I didn't really speak to this very much, but you need to have a recharge mechanism with this stuff. The morphology is controlled by stratigraphy, not process. How does water get into the ground in the first place? This is sort of one of the ideas that people kind of ignore and just assume that you already have some sort of aquifer or ground ice system in ancient Mars. That water didn't sit there and accumulate during accretion. Cometary, any kind of volatile material outgas from volcanism and stuff ends up being steam. And you have to condense that steam and precipitate it down into the surface in order to collect and build the aquifer up over time. And that's something groundwater sapping and lots of other models, including the icy highlands, don't take into account. This ice deposits episodic melting does not explain valley network morphology. There's no other supporting evidence that suggests that you have any kind of glaciation modification occurring. And then there's a mechanism required for melting. You still have to get the surface warm enough in order to melt that ice deposit away. And just like in the Arctic environments where you have occasional accumulations of snow and ice occurring, you warm that up during the springtime and the summertime. Most of the work gets done by the storms that happen, the rainfall and surface runoff that follows. Yes, you get a lot of additional groundwater surface runoff from the melting of the snow and the ice itself, but most of the work is done in those environments during the warm summer months. So if you had a transient warming event occurring on Mars, that allows you, I mean, if the surface is warm enough to melt the ice, it's warm enough to support liquid precipitation. Now, the other thing to keep in mind is the ages of the valley networks. There's been a number of different studies that have attempted to age date the valley networks. They all kind of come to an agreement that at least valley network formation shut off during the late Noachian, early Hesperian boundary. How long did those particular valley network systems last? How long were they active? That comes by looking at the actual landscape itself. There are very few instances on Mars where you have a valley network debouching into a crater basin, and there's evidence that the water from that valley network system flowed into the crater basin, filled that crater basin up, and allowed it to breach the rim and continue to the other side. If valley networks were a very long-lived event, you would expect to see them better integrated with the topography. You'd expect them to see them breaching more impact craters. You'd expect to see more of the space filling smaller tributaries. We don't see that. So for that reason, we think that when valley networks form, the climatic optimum that was associated with them was a very short-lived event, perhaps only a few 100,000 to maybe a couple of million years. Very short wink in geologic history. And we've also applied the 2D landscape evolution model that Alan Howard did, and he came up with this idea of an X ratio, which is a ratio of the net yearly lake evaporation to the yearly runoff depth from the uplands. Basically, it's kind of a way of representing just how humid the climate was. And when you run that on the simulated synthetic crater landscape, if it's too humid, you have too many lakes forming, you have too many valley network systems forming. If it's too dry, then you don't get any valley networks forming. You just have little puddles of water standing around all the place. This model suggests that the valley networks formed in a semi-arid environment, a pretty dry environment where you probably had occasional rainfall events, short-lived climatic optimum, but that was enough to get the work done and create the valley network systems that we see. So the geologic evidence indicates that valley networks morphology is entirely consistent with rainfall and surface runoff. Valley networks follow the topographies. Headwater areas originate in drainage divides. It requires large amounts of water with a viable recharge mechanism, i.e. had a hydrologic cycle and precipitation. And they were formed during a more humid climate optimum during the late Noachian, early Hesperian. So here's sort of a map showing the distribution of valley networks. What I want to talk about now are the outflow channels, which are very unique, large features. Some of the proposed processes for these features include volcanism, and I actually have a former, yeah, I know, it's exactly. I can tell you a story about a former postdoc that I had who's still advocating volcanism as a mechanism for, there's a reason he's a former postdoc. And then aeolian erosion, which nobody believes anymore. And then, of course, is the catastrophic release of water. And, you know, Vic Baker can come up here and talk about that much more intelligently than I can, but that's the accepted paradigm. That's what happened, folks. And how can you sit there and argue for an icy highlands model and ignore the fact that it doesn't give you any kind of mechanism for creating catastrophic outflow in these outflow channels that we see? Of course, the analog that we have here on the Earth is the channel scablands in Washington State. Again, I'm not going to try to take Vic Baker's story. I would just insult him, I think. But there's evidence of other types of what would be a very similar event in the origin of Maadine Valles, in that we have evidence for this sort of lake region just south of Maadine Valles, which eventually overflowed, and the easiest area to breach was right along the Maadine Valles channel. So if you look at it, it's not very obvious what the source of water was from that, but now that we have the topography and we're able to understand the climate a little bit better, or essentially understand the hydrology and the groundwater hydrology, we published a science paper back in 2002 that showed that Maadine was more than likely the result of this lake district overflowing. What's the additional evidence for liquid water on Mars? We have now, with high resolution imagery, evidence for deltas and alluvial fans forming, in particular some of these impact craters that have been breached by valley network systems. So they were carrying sediment into these systems and hitting standing bodies of water that were in these impact craters, creating these deltas. You also have the geochemical evidence now that we didn't have before. People have sat there and they've tried to suggest that you had the phyllosilicates, the clays, forming during the Noachian, and then somehow or another the climate was different during the Hesperian that supported sulfates. I think it was Kelvin that tried to do this with the Earth in some sort of geochemical model over time. It doesn't work. There's Misha Zolotov put together this great paper that was in Icarus about 2 years ago, where he showed that if you take a layer, just a stack of basaltic rock, you drop acid rain on it, what you're going to do is leach out the phyllosilicates and the sulfates, where you get the phyllosilicates on the bottom, sulfates at the top. That's probably what happened. And then we have plenty of lander data too, right? We've put landers all over the surface of Mars. And in a case of Viking, Mars Pathfinder, Spirit, Opportunity, nothing but evidence for liquid water. We don't see any evidence for ice, no evidence for glacier transported sediments or anything. It's all liquid water. And then we had Curiosity landing Gale Crater. I actually applied for a job at JPL years ago as a Mars lander scientist. And I was interviewed by somebody there who was a climate modeler who ran the Mars program, and at the time I was advocating warm, wet, early Mars. I said, well, what kind of evidence would you look for if we put a lander on the Martian surface? And I went through, phyllosilicates, or, the sedimentary deposits, alluvial fans. And as soon as I said alluvial fan, he laughed at me. I knew I didn't get the job, which is okay. I'm okay at the Smithsonian. But then Curiosity lands on an alluvial fan, right? And when we looked at that deposit, you look at the the material that was transported as part of that fan building process, that little boulder over there requires something on the order of water that's hip deep. Lots of water going across that surface, transporting that sediment. And then you had work that both Dave and Jeff have done recently, looking at standing bodies of water there in Gale Crater, and their idea that you had some sort of semi-arid climate fits with everything else that we've done before in the past. You know, some precipitation, still pretty much a dry environment, but it explains the morphology and the evidence that we had for standing bodies of water in Gale. And then you have what people have proposed as shoreline features. And if you look at some of these features, at least one set of them actually follows the topography, suggesting that you had a standing body of water in the northern plains of Mars, which is almost necessary, almost predicated on establishing any kind of hydrologic cycle that would have fed the precipitation required to form the valley network system. So the evidence is coming together. Our current understanding is basically this. During the Noachian, you had modified impact craters. They indicate a long-lived arid environment. Now, they were getting eroded, but they weren't forming valley network systems. It was an arid environment. You had some water around. It was capable of moving eroding the craters and moving sediment, but not enough to form the valley network system. That didn't occur until about the Noachian Hesperian, where you hit this climatic optimum, and then you were able to raise the humidity a little bit and form these valley network systems. Later on, during the Hesperian, you were able to form the outflow channels. Basically, all hell breaks loose. You have large amounts of standing bodies of water now, perhaps even a northern ocean. I'm all for that. And then during the Amazonian, Mars dies. Early Mars had to have been warm and wet. And climate modelers keep pushing back at us, but the geology is the empirical data. Their output is the theoretical data. The empirical data should be the thing that you go to explain any kind of model output. And the fact that they've been ignoring the geologists for so long is really frustrating. I'm sure a lot of people in this room would agree with me. So what does this imply about the atmospheric conditions? Can you extract anything from this? I think you can. As an example, Ralph Lawrence and I did this paper last year in Icarus where we looked at what does the work implied from the geology suggest about ancient climate conditions. Basically, you know, a raindrop has to hit the ground fast enough not only to do some work, but to exceed the infiltration capacity of the soil. And what we were looking at here is just how much work could you do at different atmospheric pressures that have been proposed for explaining the early climate of Mars. And what we found that if the atmospheric pressure is greater than 4 bars, then what basically happens is you don't get much work going on at all. You have sort of a fog-like environment that's really incapable of doing much erosion. Now, it might, you know, kind of do some chemical weathering of whatever rock is exposed, but it doesn't really hit the ground fast enough, hard enough to do any kind of work. The optimum conditions occur at about 1.5 bars, where now you can generate storm-like conditions. You can drop rain hard enough, fast enough onto the surface of Mars to exceed the infiltration capacity of most basaltic materials to initiate surface runoff and do the work necessary to do the channel incision that you see associated with the valley network systems. So what we're suggesting is one possibility why the Martian climate seemed to have changed at time is that you started off with a primordial steam atmosphere of about 4 bars. As you condensed and precipitated that atmosphere, maybe lost some of it to space, the atmospheric pressure dropped with time until you got to about 1.5 bars, and then all hell breaks loose. But Mars is starting to die right now, right? The atmospheric pressure is waning very quickly. It's getting eroded. It can't maintain it, and it collapses, and you end up going into the Amazonian. Why is any of this important? Well, we're all geologists in the room, or at least most of us, right? You look at the time scale for the Earth. Life began about 4.5 to 3.5 billion years ago. In fact, it's probably later than earlier. If you look at the geologic time on Mars, what we're talking about really are processes that occurred during the Noachian. So What this implies is that the same geologic processes that were operating on Earth when life started on our planet, were also operating on Mars. And that's important because if you look at where we have geology exposed from that period in history, there's not much of it preserved on Earth. We've lost it through plate tectonics and erosion. On Mars, however, about half of the surface of the planet is covered in these rocks that date back to that period in history, again, when life is starting on our own planet. So these early solar system processes that have been pretty much eradicated on our planet are still preserved on Mars. Now, does that imply that you had life on the surface of Mars? I have to be careful what I say here right now because my son is a freshman at Virginia Tech and he's studying biochemistry with the idea that he wants to go into astrobiology, which is cool. But I would argue that we don't have any evidence for life on Mars at all. All right? We have better evidence for Bigfoot, as we got footprints and maybe even a really cool video footage of Bigfoot walking around. We have maybe even better evidence for aliens on Earth because all these cool UFO pictures and even an alien autopsy photograph. We've been to Mars multiple times now, and the astrobiologists keep telling us that life is always over the rock that we didn't turn over, or the hill that we didn't explore, or underneath layers of regolith or something like that. It's not there. What these extremophiles tell me is that people that study life in ice or underneath Lake Vostok in Antarctica or something, is that once life starts on a planet, you don't really need to look very hard to find it. It's everywhere in every environmental niche possible. And we've looked at plenty of environmental niches, and if life started on Mars, it's had 3.5 billion years or more to adapt to those surface conditions. We should see it by now. But the point I think we need to be conscious of as a planetary science community is that finding the prebiotic chemical elements that went into creating life on our own planet is probably just as important as finding life on another planet, because that record is gone on our planet. It was like a match went off. That chemistry is gone, and now I'm the flame up here, you're the flame, our dogs and cats and the trees and the birds in the air, they're all the flame from that one match that was lit when life started on our planet. The unlit match is sitting there on the Martian surface, probably someplace. That in and of itself is worth exploring Mars. So what are some of the outstanding questions? These are just some that kind of came off the top of my head. Again, we need to look at spatial and temporal differences in valley networks and modified impact craters. We're taking it all together as they're all just one process involved, and I can tell you it wasn't. And the idea that you might have some ice melting in some place to form valley network system is completely plausible in some of the areas. The possibility you have groundwater sapping occurring in some areas is completely plausible in some areas. We need to understand the spatial and temporal variations in these processes that occurred in time. They got this huge geologic record sitting there waiting to be deconvolved. And we're starting to do a little bit of it, but it's a lot more difficult than you think it would be. Deltas and alluvial fans. Those sediments on the Peace Valley's fan that I showed you in Gale Crater, it's really hard to generate sand from a basalt. Basalt exposed to the surface, exposed to the element, wants to break down to clays and flake off into clays. It doesn't want to break down into sand-sized particles. It typically doesn't have any phenocrysts in it. It's usually aphonetic. How do you get sand in coarse-grained particles from a basaltic rock? That's one of the things that we're working on, and that's one of the things I'm doing in Hawaii. It's just understanding how basaltic material comes into existence, but also what happens to it as it's transported by different geologic processes. The basaltic weathering is the sources of the sediment, again, for the deltas and alluvial fans, but everything else we see, the sand dunes and the dust in the air, everything on Mars, and it's also going to influence the morphology. That sort of sharp slope that I showed in the modified impact craters, that's really hard to do. If you have a stack of material and you're weathering it and you back waste it at about 2 kilometers, you should generate a lot of sand-sized and gravel-sized material, and that should form some sort of fan down here at the bottom. But in a lot of instances, we see, again, like God came along with a cookie cutter and just punched a hole in the ground. Why is that? What's happened there? Where's the sediment? How's that material eroding? Little things like that, guys, still need to be answered. So there's still a lot of work to be done on that. I don't have the chance to work with many graduate students at the Smithsonian, but if any of you guys are interested in that and you have your support from an advisor here, we can look at ways of supporting you through a pre-doc or even a postdoc position at the Smithsonian. But if you just want to work with me on some of these ideas too, or just talk to me about some of the ideas I have that I'm not mentioning here, I'm all for it. I like the opportunity to work with graduate students. Again, I'm not going to live long enough to see all my ideas ever come to fruition. So that's all I had today. I appreciate your attention.
Questions for Bob? Yeah, go ahead.
It sounds like from the crater evidence, your models that with the fluvial activity explain sort of flat floor and climate. Are you arguing then for a period of hundreds of years or longer where it was able to work on Mars? And but then something even much more extreme than that led to the valley networks?
Yeah, that's exactly what we're arguing for. So basically during the Noachian, you had a pretty arid environment. Now, it doesn't mean that it rained like every day or even seasonally, but you had periodic episodes of rainfall events that were capable of modifying the impact craters. Yes, and that wasn't obvious to me. In fact, I was kind of upset when Alan Howard came to me and said, well, he showed me the evidence that valley networks didn't form contemporaneously with the modified impact craters, and that we're talking about a different climatic event. But that seems to be the case now, that if it was more humid, then we would have gotten a lot more valley network systems forming. We would have had the space-filling tributaries forming, better integrated with the topography, and it's just not the case. So. Yeah, it doesn't work, and I probably wasn't clear enough in my talk, but the fact is you see craters modified anywhere from a little over 5 kilometers in diameter all the way up to the largest impact basins that we have on Mars. And they're preserved in different stages of modification. So what that implies is that you had the same sort of modification processes occurring over time that was continuing as the new craters were forming throughout the Noachian. Otherwise, everything would have been, it would have scaled to crater diameter, but everything would have sort of been preserved at that sort of one stage of crater modification. And that's not what we're seeing. So it was a long-lived event. Again, I can't tell you that it happened every day, but it happened at least to the periodicity so that it looks like it was a continuous process. So you can't really separate that geologically. Yes?
Intrigued by seeing the mass wasting equations I've seen since undergrad geology, but you were saying how that would affect what it can transport on Mars, preferentially smaller grain size?
Yeah, I can show you some outputs that we did, but basically that equation that P is as Meyer, Pierce, Muller, and then Einstein's son actually did some empirical work with different sized particles, and the coefficient changes depending on the grain size of material. And so, the only real difference with Mars being gravity, what ends up happening is that, silt-sized particles, you have the cohesiveness of those smaller particles. That's still important for Mars as it is on the Earth. But as you get to the sand-sized particles, you get a little bounce from the lower gravity on Mars. Basically, the sand-sized particles just don't weigh as much, so a stream is slightly more efficient at carrying the sand-sized particles. But then what's happening is that as you get to the coarser grain particles, say about pebble size or larger, then it's the weight of the water that becomes important. So you're not getting the shear stress that you need to compensate for the lower gravity because the water doesn't weigh as much. So it becomes equivalent. The effects sort of cancel each other out.
I'm sorry, I wanted to know if you see that in the data.
Well, it would be kind of hard to see necessarily. And basically all it's arguing is that the streams would be more capable, more efficient at carrying sand-sized material. And unless you really have transport limited conditions, say like out in the streams in Australia where you know, the shape of the channel is sort of controlled by the shear stresses generated with all the sand that you're transporting, you're not really going to see much of an effect. And again, we don't, you know, we're looking at valley systems. The valleys were formed by the channels that went through them. And there's very few instances where we see even channels preserved. I mean, there are a couple of dozen now, I think people have identified. But, you know, there's been some degradation that's occurred after that formation has, and, you know, we don't see many channels. And that would be the place to look for that effect. And maybe the deposits too, but, you know, it's just a neat thing. It's not, you know, it's not going to change the world.
Heavy crater, the order of 100 million years old, and it's covered with channels. All over the interior of the crater, right up to the peaks, right in, all over the ejecta. There's no erosion on adjacent landforms. It's just the ejecta that's eroded. It's nowhere near the Milwaukee-Bearing boundary. How do you explain that?
You remember that classic film, Alfred? Scientists just don't know. You know, Mojave Crater, and actually, you know, some of the alluvial fans that we're seeing on Mars too. I think what's happening is that's evidence for ice deposits melting, and I'd have to look closer at Mojave Crater, but at least some of the alluvial fans that we've been examining on Mars come from these little alcove systems, which would be an ideal place for ice to accumulate over time. And
These channels in Mojave are on the ejecta, far from the crater. There aren't steep slopes.
well, the other possibility is, you know, the Teresa-Segura model, where, you know, during the formation of that particular crater, you released a lot of surface water, and you had a local transient event where you dumped a lot of water that was sequestered in the regolith into the atmosphere. I haven't seen a convincing model, though, that really supports that.
Right, and I think it would have eroded nearby adjacent landforms. I think the ejecta itself was wet, it landed and eroded. That's what I think has
So it basically, it was wet ejecta, and then it just released, okay.
just made those channels as it was deposited. And
Alfred, that's...
that can explain a lot in Milwaukee as well.
well, but you have to get the water into the regolith in the first place.
I don't know how to do it.
Yeah, well, but see, again, that gets to my suggestion that we really need to look at the spatial and temporal variations in crater morphology over time. Because, you know, we're treating this as it's sort of a universal problem, and it probably isn't. There were variations, regional, elevational, latitudinal variations that we don't completely understand right now. And that's, you know, probably a really good example to show what it is that we still don't understand.
Yeah, that's my suspicion about much of these debates about Mars. We're missing something fundamental in terms of understanding these problems.
Yeah, still lots of work to do. But it's not the Icy Highlands model.
Well, if there's any more questions, we can answer them just in discussion. Let's thank Bob one more time.